Hello, we are going to start this webinar. We have had several technical problems, but we are going to start now. This webinar about spatial tools for evaluating woody debris flooding hazard in gvSIG. It will be given by Silvia Franceschi from Hydrologies and the gvSIG Association. So, Silvia, whenever you want.
Okay, thank you, Mario. Thank you for your introduction. So, welcome to this presentation and good morning, everybody. I'm Silvia Franceschi, and I'm an environmental engineer specialized in hydrology, hydraulics, and geomorphology. I am a co-founder of the Hydrologists team that is a small engineering company based in the northern Italy, which is now part of the member of the gvSIG Association. This year, I'm also finishing my PhD here in Italy in mountain environmental and agriculture, and I am also an OSGeo charter member. So this presentation is about the hazard, the problems related to wood in rivers during flooding events. So let's start to introduce the problem. In mountainous regions, and especially in the Alps, basins have been impacted by humans since ancient times. For example, in Europe, since the First World War, forests were regularly and heavily harvested, mainly for timber and firewood production. And usually forests were eliminated to create spaces for pastures, livestock, and agriculture. But in the last century, with the decline of the rural and forest economy and the depopulation of mountainous areas, the forest became old and the shrubs and trees encroaches abandoned crops and pasture lands. For example, between 1880 and 2000, the average increase of woodland in Switzerland has been greater than 20%. In general, the presence of vegetation influenced the water cycle, starting from the runoff production, the evapotranspiration, the possibility to erode the soil, and to mechanisms of transport and deposition of sediments and also of wood. From one hand, this riverside vegetation is very important for the ecological point of view because it maintains the biodiversity of the local environment. But on the other hand, this vegetation can produce problems due to the transport of sediments and to the transport of the logs, especially during extreme flooding events, when the flow overflows the banks and goes to recruit the vegetation outside the river. So we need to balance these two main aspects, the ecological aspect and the risk aspect. So we need tools to give to the decision maker the possibility to get informed decisions, to balance these two aspects. So the object of my research is the development of a GIS-based tools for predicting the magnitude of the large wood transport during flooding events at any given section within a river basin. Basically, I consider two main processes related to woody debris: the large wood recruitment from hill slope instability and from bank erosion, and the large wood transport and propagation of the logs downstream the river network. Regarding the large wood recruitment, one of the most important variables that we have to evaluate is the area that provides large wood. This area can be evaluated as the sum of the area interested by the channel widening, and so therefore the bank erosion, and the area and the unstable slope connected to fluvial network. So the area of the hill slopes that can contribute to the instability. On these areas, we have to evaluate the presence of vegetation, because in this case we are not considering the all the sediments coming from the hill slopes, but we consider only the woods, the logs that can come and reach the rivers. So we can calculate the available vegetation using empirical models based on the canopy height model and the forest stand volume, or using more precise models and algorithms based on the single tree extraction on high precision LiDAR data. In this case, we can extract the position and the characteristics of each single tree inside an area, characteristics like height and diameter at breast height. So, putting together these two information, the area that provides large wood and the availability of vegetation in that area, we can estimate the volume and dimension of available large wood in each section. Then we need to propagate these logs downstream. So we developed a one-dimensional hydraulic model based on the San-Venant equation, which consider the sections of the rivers extracted from the digital terrain model and some other parameters, important parameters for the propagation of the woods, like the presence of bridges and dams, and connect this information with some data collected in the field by other kind of monitoring of the environment. So by propagating the logs for each section downstream, we can highlight the critical section, so the clogging section, and the volume of the wood that can accumulate in each of these sections. This is a schema containing all the inputs and outputs of the model. For example, we use many inputs, raster maps related to the derived from the digital terrain model, like the flow direction, slope, total contributing areas, and the downslope component of the connectivity index, a shallow stability model, and so on. Then we need some information about the superficial geology, if there is rock or not, and the vegetation, like the forest stand volume or the presence of single trees, and some hydraulic parameters, like the discharge, the presence of bridges and check dams. All of these to get as output the places where the logs comes from, so the sources of the logs, and to highlight the clogging or critical section, and evaluate the volume of the deposits in each of these critical sections. This model that I described has been developed in the JGRASS tools library, and now integrated also in gvSIG, and it is split in sub-models, and following a step-by-step procedure, starting from the pre-processing of input data, the evaluation of the attributes of the stream river and of the hill slopes, and finally the mechanisms for recruitment and propagation of the logs downstream the river network. Let's see some of these modules in details. So first of all, this GIS model should be with this GIS model, it should be possible to apply the model to an entire basin and not only to a single reach. So we need, in any case, to have the possibility to know exactly the position of each single section and the position of each single log in the river. So we need some tools to navigate the network, basically based on an hierarchical enumeration of the network. We used some for this hierarchical enumeration of the network. We used some of the JGRASS tools, already existing tools in the JGRASS library, which is the hierarchical attributes, calculating the enumeration following the Strahler order, the hack length, and the Pfafstetter order. To evaluate this enumeration, we need some geomorphological DTRM derived attributes like the network of the raster layer, the map of flow directions, and the map of topside contributing areas. So this is an example of the integration of the tools in the JGRASS tools library, and in particular these ones of the large foot recruitment in gvSIG. As you can see here, you can select the module, and on the right side of the window, it will appear all the necessary input and output, and also the parameters. If you run the module, you can get the map or the output directly in gvSIG, loaded directly in gvSIG. And in this case, we have the enumeration of the network following the three different enumeration schemas: Strahler, Hack, and Pfafstetter. Then another problem that we faced is the evaluation of the possibility to erode the banks. We can say that there is the possibility to erosion of the bank if there is not a rock, and if the flow is higher than the normal flow. So the flow erodes, the flow overflows the normal banks. So we need to understand which is the area where the water normally flows, and this area is called bankfall area, or bankfall width, and it corresponds to the stage, the width corresponding to the stage at which the water overflows the natural banks and begins to inundate the uplands. And usually, conventionally, this is related to a flow event that with a recursion every 1.5 years. Usually, we get some polygon of the extension of the bankfall area, and this can be can derive from field surveys or satellite or remote sensing imagery. And and then we have to assign to each of the river section this bankfall width. There are some problems in this assignment because we have different origin of the data. Usually the river network that we use is the one extracted from the digital terrain model, and the position of the bankfall derives from orthophoto or satellite images or from the field. So there are different possibility that the network is correctly inside the bankfall polygon, or the network is tangent the bankfall polygon, or in some cases also we have problems where the network appears outside the bankfold polygon. To face this problem, we developed some tricks inside the module, and some parameters in the graphical user interface are required to the user to adjust the extraction of the section to the available data. And this is an example of the output. As you can see, this is the extraction of the single of each section. As you can see here, the section were outside, the river network were outside, but the sections were correctly delineated. And the width corresponding to these sections are added as attributes to the points of the river network. And so it is possible to visualize a map of the reaches with a color related to the width of the section, in this case, like in this case. Another important parameter regarding the hydraulic side of this tool is to consider the presence of structures. Usually where there is a structure, the width is maintained fixed during the flooding events, because there are dams, and in particular where bridges or dams are present, there is no possibility of widening, because the dams are fixed and constructed, so there is no possibility of erosion. And also, if there is a dam or a bridge, we know exactly the dimension of this structure, because we have the design, the projects, and so on. So we also developed some tool to correct the width of the section, calculated as before, with the information that we can have on some particular structures. And also we have to consider that we cannot have bank erosion in these sections. Regarding the bank erosion, this is proportional to the, this is calculated using the width ratio, which is the ratio between the width after and before the event. And this width ratio is conventionally calculated following a power law of the unit stream power in the pre-event condition, where the parameters of the power law are derived from field observation and are input parameters of the model. For example, as you can see here, the width ratio is proportional to this power of the unit stream power, which is this omega, and the unit stream power is a factor which considers the discharge, the slope, and the width of each section. So gives the the feeling of the power of the flow in that section. And then we have to consider that the bank erosion, so widening, is avoided where there are structures and where there is rock, because we can insert also a layer of geology where we fix some deposition of the rock in surface. This is an example of the output. In magenta, you can see here, these are the bankfold sections, and the widening area, so the maximum extension area, considering that discharge is this is the one in cyan, and all this information are added as attribute to the point of each section in the shapefile of the sections. So this was for bank erosion. Then we have to consider the contribute of large wood from hill slopes. We decided that only shallow landslides on connected areas deliver logs to the channels. So we have to evaluate the amount of wood that are present in the unstable and connected areas. So first of all, we have to evaluate the amount of the vegetation, the presence of vegetation. And this can be evaluated using some empirical models based on a canopy height model and total stand or forest stand volume, or following a single tree approach for the extraction of single trees from high precision LiDAR data as point cloud, or again, canopy height model or digital terrain model, high precision digital terrain model. And from this model, we can get some vegetation parameters like the position, the height, so that which give us the idea of the length of the logs, and the diameter of the trees. This is an example of the extraction of single trees on an area done with some tools that we also developed and integrated in the JGRASS tools library. And for each of these tool tree, there is the position is known, and also the height of the tree. From the height of the tree, considering the species, we can evaluate the diameter of each single tree. Then we have to evaluate which are the unstable connected areas. So we need a shallow stability model for hislop, and we use ShallStab in this case. And then we connected also the information about the downslope component of the connectivity index, fixing a threshold over which the pixel is considered connected or not. So this is an example of the map of the connectivity index. As you can see here, it is very similar to a map of the distance of hislop's distance to the network, but it is weighted considering the stability of the pixels. So basically, if a pixel is unstable, it is more connected to the river network. It is easier from that place to go to the river network rather than from a stable pixel. And this is the map where we highlighted the subbasins for each single section of the river basin. So for each single section, we know the area and the condition of stability and connectivity of this area. So from this information connected with the presence of vegetation, we can evaluate the large wood contribute in each single section. As you can see here, only the triangles, the trees that are triangles, green triangles, are those that can reach the river section for this event. And here you can see them better. So from all the trees, only these trees will reach the river during this event. And for these three are connected to the section where they are going down. And we can, therefore we can evaluate a map like that, where for each single section of the river we have the amount of wood that is that can reach the river coming from the hillslope, the local hillslope. So now that we have the wood in each section of the river, we can go on with the propagation downstream of these logs. The large wood is routed downstream using a simple Boolean transport condition based on the ratio between the length of the log and the width of the sections, and the ratio between the diameter of the logs and the water depth. All these two ratios are input parameters, so can be defined by the user and can be different for the length and for the diameter. Then we have to evaluate the post-event hydraulic conditions, like the channel width and the water depth. And these are calculated using the 1D hydraulic model based on the peak discharge. In this way, we run simultaneous the 1D hydraulic model and the check between the simple Boolean conditions, so to identify the critical section of the transit of large wood in the stream network. And in this case, all these crosses, red crosses, are critical sections, and in the attribute tables you can find all the attributes like the width, the slope, the volume and height, and dBH of the contributing hill slopes, and if this section is critical for the transportation coming from the hill slopes, the local hill slopes, or from the upstream sections. And here is a result of the application of the model to a very small basin in the upstream section, where there are big trees and small sections. Critical sections downstream are usually connected to the presence of a dam, a bridge, or a structure which reduce the possibility of channel widening. So this is what we developed until now. Even if I am concluding my PhD, we are considering to go on with these important tools, because the presence of wood is very important and it increases the hazard of flooding in all over the world. So we are planning to integrate the possibility to use the section from field surveys and not only derived from DTM, and to run automatically the tool for all the basin, not only for single reaches, considering the Pfafstetter enumeration of the river section of the river network. So this is all for now, and thank you for your attention.
Thank you, Silvia.
Okay.
There isn't any questions, so it seems that it's very clear. The presentation is very clear. So if there is any question later, because the webinar is being saved, if it is being recorded, if you are not seeing the webinar live, you can ask any question about the presentation at the mailing list, the users mailing list, where Silvia is registered. So you can ask at the mailing list. And thank you very much. We are going to finish this webinar, and we will continue with the next webinar of the second gvSIG festival. Thank you very much.